Let's look in more detail at heat energy, or the thermal radiation that results from objects at room temperature, or planets, or people. This is a familiar regime in astronomy because we'll be looking at planetary science and cool objects adjacent to stars. These objects will emit infrared radiation. And because we have the technology to make images with infrared radiation, it's clear that we can view infrared radiation in the same way that we view visible light.
These days we're all familiar with night vision cameras, but how do these things work? How is it that you can just turn on this camera and see the invisible? Another use of night vision cameras that you might not be familiar with is their ability to see through smoke and dust. Fire departments commonly use cameras like these to find people trapped in smoky rooms, or to pinpoint the exact location of forest fires through clouds of smoke. So how do these things actually work? What are we really seeing when we look inside a night vision camera? Well, it may surprise you to learn that everything in the universe emits some kind of light. It's just not the kind of light we're used to thinking about. The sun, for example, our star, emits visible light. That's why our eyes evolved to detect that kind of light. But that's not the whole story. I'm sure you're familiar with all the different kinds of visible light, all the colors from violet to red. But there are actually lots of other kinds of light that our eyes aren't sensitive to. The reason all the colors of light are different is that they have different energies. And what you see here is that the light has different wavelengths. The blue light, for example, has a higher energy, so it has a shorter wavelength. The red light, on the other hand, has less energy, so it has a longer wavelength. But that's just the light we can see with our eyes. That's not all there is. The shortest wavelength light are gamma rays, which can have wavelengths smaller than an atom. The longest wavelengths are radio waves, which can have wavelengths larger than the entire Earth. The kind of light an object emits depends on its temperature. We're used to thinking of something hot giving off light. But it might surprise you to learn that objects that are cooler, like myself, give off a kind of light too, and that's what a night vision camera can pick up. That sort of light is called infrared light. The world sure looks a lot different in infrared light. Remember that what you're actually seeing is temperature. So something that's warm is going to look bright in the infrared. And something that's cold looks dark. Ice cream. Blow dryer. And infrared radiation is actually a measurement of temperature. Places on my face that are cold, like my nose, appear dark in an infrared camera because they're giving off less infrared radiation. And places that are warm, like my mouth, or the hair next to my head, are brighter because they're warmer. You can even see my breath in my nose if you look carefully. And this is an ice cube. And humans, of course, are not the only things that emit infrared light. What do you think you can learn about animals by observing them in the infrared? What about reptiles? Remember, they're cold-blooded. Giraffes. Here's a Nubian ibex. What do you think horns look like in the infrared? Can you even see a gorilla in this picture? If you look carefully, you'll notice you can still see the zebra's stripes, even in the infrared. How about elephants? What about a polar bear? How about a rhinoceros? Check out the horns. A cat. Notice the infrared footprints. Deer in the dark. A helicopter. Notice the plume of heat from the engine. Earth movers with hot smokestacks. A car engine turning on and heating up. Infrared light also has a lot of really interesting properties that visible light doesn't have. For example, it can often pass through things that block visible light completely. But just like infrared light can penetrate some things that stop visible light, it also gets stopped by some things that let visible light through. For example, here's a piece of glass. And as you can see, none of the infrared gets through at all. If you haven't guessed, that's how the greenhouse effect works. Infrared light can't get through gases like water vapor in our atmosphere, which means that the heat is trapped and our planet is getting warmer. So what am I, an astronomer, doing with an infrared camera? Well, if everyday objects look different through an infrared camera, you can bet objects in space do too. For example, here's an image of the constellation Orion, which you're probably familiar with from the night sky. But now, let's look at it through an infrared camera. Look how much you're missing. Astronomers are also hoping to use infrared light to find planets around other stars. Planets don't give off any visible light of their own, making them nearly impossible to see close to a bright star. But in the infrared, planets give off their own light, making them much easier to find. Astronomers will soon be able to use very sensitive infrared cameras on a new space telescope, the Space Infrared Telescope Facility. And it should give us a whole new perspective on the universe. At that point, we'll finally be getting a more complete view of the universe. Right now, we don't even know what we're going to discover. There are so many wonders out there. We'll finally be able to see more than our eyes can see.
We're going to see a series of pictures taken with a thermal imaging camera. This is a camera like the detector in your cell phone, which images visible light, only in this case it's sensitive to waves that are 10 times longer than the eye can see. So these are detectors which make images of invisible radiation from cool objects and show the temperature of these objects, which otherwise wouldn't be visible to the naked eye. In the top picture here, there's a warm and a hot cup of water. But you can't tell just from their color which is hot and which is warm, until you view them with an infrared camera, where the highest emission will come from the hot object, and the lowest emission will come from the cool object. In this pair of images, you can easily tell the difference between a cold-blooded animal and a warm-blooded animal, based on infrared imaging. It's easy to tell the difference between a hot tap and a cold tap with this camera. And look here at images of human faces. It's quite a different view of a person compared to an optical picture. Familiar materials also operate differently to these longer waves. If you had a sheet of dull aluminum, it would not reflect visible light. It would make a bad mirror. But if you pointed it at an infrared camera, it would make a perfect reflection of your face, because the surface is smooth as seen to infrared waves. So mirrors operate differently in the infrared, and materials are different in their transparency properties. In this pair of images, we can see that a black polythene bag, which is opaque to visible radiation, is transparent to the longer infrared waves. The point of these pictures is that we can do just the same things that we do with visible light with infrared light. Infrared waves are just 10 times longer. We can focus them, we can image them, we can reflect them, and so on. Here's a little experiment. Imagine you wrote with different colored ink on a white background a word. Based on sunlight or natural light illuminating this page, which would be the hottest? Which color of ink would glow the brightest in infrared radiation? See if you can guess the answer before we see it. Now, infrared radiation is extremely valuable in astronomy, and we'll be seeing many examples of this. The universe looks quite different to infrared radiation than it does to visible radiation. One of the most dramatic examples of this comes when we look at any region where stars are forming. Star formation regions are mixed with gas and dust, and that dust in particular is opaque to visible light. But the longer infrared waves travel freely through it, which means that we cannot see into a star-forming region with a visible telescope. But with an infrared telescope, we can see all the way to where the stars are forming. So infrared astronomy is a valuable counterpart to optical astronomy, and it was in fact first developed in the 1970s. It's not just infrared radiation. Across the electromagnetic spectrum, we see different views of the universe through different wavelengths of radiation. Here are views of the Sun across the electromagnetic spectrum, showing that actually in the optical view of the Sun, with just a few sunspots, it's fairly quiescent and dull. But as seen in both higher and lower energy forms of radiation, the Sun is quite dynamic, because it has cool active regions and extremely hot active regions. And here are a set of views of the Milky Way, the disk of the galaxy, seen in all directions in a strip along the sky. This shows how different our galaxy looks as seen to the different wavelengths of electromagnetic radiation. As with the star-forming region, as seen with visible light, the Milky Way is ragged and obscured by dust. That's what you see with your eye on a dark site looking at the Milky Way. If we want to see the true pattern of stars in the disk of the Milky Way, we have to go to the infrared. And in the infrared views, the very thin disk of the galaxy is clear. We can also see clear to the center of our galaxy, some nearly 30,000 light years away. At higher energies, we see other phenomena, such as the violent deaths of stars in supernovae, or compact objects like neutron stars and black holes. Here are a set of familiar objects imaged with infrared cameras. See if you can recognize what they are. And here are the kind of things we're learning with our first deep and sensitive surveys of the infrared sky, where we use infrared detectors to make the same kind of images we've been making for decades with optical telescopes in space.
WISE is the Wide Field Infrared Survey Explorer. WISE is going to find hundreds of millions of objects spread over the entire sky, and for us, that's like a treasure map. We think there are about as many grains of sand on this beach as there are stars in the entire universe. So the task of finding rare objects in the universe that we're interested in requires the maps that WISE is going to make. It's a bit like using this metal detector here to try to find gold coins that are buried in all of this sand. WISE consists of a fairly modest-sized telescope, about 40 centimeters in diameter, that would sort of fit under your arm. WISE is going to survey the entire sky in 4 infrared wavelengths over 6 months. All-sky surveys are one of the basic tools that astronomers use to find interesting and unusual objects. It's sort of like the GPS of astronomy. One of the most exciting things that you expect to find with an all-sky survey like WISE is the unexpected. We expect surprises, things that we have no idea about today. One of the projects WISE is going to be doing is studying the population of near-Earth objects. These are asteroids and comets whose orbits get close to Earth's orbit. Now, this doesn't necessarily mean that they're going to hit the Earth, but we do want to pay some attention to them. With WISE, we'll be able to tell something about how many there are, what their sizes are, and what they're made out of. Whether they're soft and crumbly like this ball of sand or solid rock like this rock right here. In visible light, an object that's small and shiny reflects the same amount of sunlight as an asteroid that's big and dark. But when we look with an infrared telescope, we're seeing heat that's emitted from more sides of the asteroid, so we get a much better true measurement of the object's size. And this is important because it allows us to tell whether or not we're dealing with an object that's this big or an object that's this big. The maps that WISE is going to be generating can be used to find all sorts of rare and unusual objects. One of these objects is the most luminous galaxy in the entire universe. But finding it is about like trying to find one particular grain of sand on this entire beach. One of the other rare types of objects that WISE may find is possibly the nearest star to our Sun. We think that there's a good chance that our Sun actually does have a closer neighbor than we already know about, and it's likely to be a very cool type of star called a brown dwarf. The temperature may be room temperature or even colder, maybe as cold as an iceberg, say.
With WISE, we expect the unexpected. We're looking for new surprises and new discoveries. And with this exciting survey, we're going to be finding a treasure trove of discoveries that astronomers are going to mine for decades to come.
Heat energy is a good example of other invisible forms of electromagnetic radiation because we have the technology to make images with heat energy and see it as if we would do optical light. Remember, these waves are 10 times smaller than our eye can see. But we can see that heat energy, just like visible light, can be focused, reflected, and used with telescopes to learn about the universe. It turns out that infrared telescopes are particularly useful in seeing deep into the regions where stars form and giving us a complete view of the architecture of the Milky Way, amongst other things.